Is it recording? Yeah, it's recording. Okay. Cool. Okay. So problems aren't too long this week, so I think we'll be fine to just go through all of them. So I won't bother asking you which one to prioritize, since we most likely will be able to get through it all. Okay, so let's look at problem 1. So trailing the last topic, spinors from the Dirac equation. So here we're considering the poly-Dirac representation for gamma matrices. So that's just representing gamma matrices in terms of the Pauli matrices. And the wave function of a helicity eigenstate psi equals the v or nu up e to the ip mu x nu x mu. How do we interpret this spinor eta that's defined as this I times gamma 2 and times the adjoint transpose adjoint spinor of this eigenstate? And hint, an overall phase factor does not have any physical significance. So that's generally like a like something that you can lean on in a lot of these particle physics stuff, that if you have some kind of U1 phase, you can ignore it. Okay, let's just look at this. So starting with the eta term. So eta, in this definition, I can write it out, rather than having this adjoint spinor, I'll just write out in terms of the charge, the conjugate spinor, and then the gamma naught matrix to make it easier. So gamma 2 and then gamma naught, and then we have the conjugate transpose. Okay, and then we're going to use this psi definition here to write out this conjugate transpose. So we get I, gamma 2, gamma naught, and then we have this V spin up, but conjugated, and then we have e to the minus I px. I'm going to ignore the Lorentz indices. So it's implied that this is a sum, but we're not going to touch this term. So I'm just going to save time writing it out. Okay, so now we'll write down gamma 2 and gamma naught in the Dirac representation, so with the Pauli matrices. So this will equal I, gamma 2 will be 0 sigma 2, 2, and then minus sigma 2, 0. And then gamma naught will be the identity matrix. I2 just means the 2 by 2 identity matrix. And 0, 0, minus I2. And then we have this spinor still, and this e to the minus IPX. Okay, and then just gonna multiply these two matrices together and take out a minus. It's gonna be a minus sign in there, so then I'm gonna take that out front. So I end up with minus I 0 sigma 2 0, and then V up star e to the minus IPX x. Okay, now that I want to write out this in terms of the two spinors as well. So if you remember from the lectures, V up is this, I always forget what this one's called. Psi, something. They're really hard to draw one. One like that. And in this case, it will just be this, but each one of them will be starred, so conjugated. So we're going to end up with minus I 0 sigma 2 0. It's that one, both starred, and then e to the minus IPX. Okay, and then now just multiply these through, then each one of them will just pick up a factor of minus I sigma 2 as a coefficient. So you get minus I sigma 2, 1 star, minus I sigma 2, 1 star. Px. Since the two components are the same, so I'm just going to work on one of them and just show you what happens. So here, using just the definition of what sigma 2 is with the Pauli matrices, and you can see that minus I sigma 2 1 star is 0 minus 1 1 0. I think sigma 2 is 0 minus I 0. So then the minus I, when you multiply it in, just gets rid of it, makes it 1 instead of I. And then record the definition for this psi as well. So it's a two spinner. So it's a 2-component vector, and it will be cos theta on 2 and then sine theta on 2. But then you're gonna because it's conjugate, so you're gonna change the sign of this complex phase. Whereas in the normal definition for xi1, you just have e to the I phi. But that's it. And then when you multiply these through, you're kind of flipping the 2 components. So this matrix just makes this one go on top and that one go on bottom. So then you end up with minus sine theta on 2 e to the minus I phi, and then cos theta on 2. And if you look at this, it looks very close to the psi2 vector, the psi2 spinner. And we can just take out a factor of e to the I phi. So if I take out e to the minus I phi at the front, then I end up with minus sine theta on 2 cos theta on 2 e to the I phi. And this thing is psi2. Yeah, so, okay. So then this minus I sigma 2 xi1 star is just equal to e to the minus I phi psi2. So both of these components just look like that. So you get e to the minus I phi out the front, and then psi2. This is number 2. And then e to the minus IPX. Okay, and the hint basically is telling you that when you're trying to interpret this, you can completely ignore this e to the minus I phi. It doesn't really tell you anything. It's just a additional complex phase and doesn't change the physics. But if you look at what we started off with, which we started off with the psi1 vector, because if I just look at the definition of this psi, and then the v spinner, then I'll just get 2 without the star. So we get the xi1 spinners. And that represents the positive energy solution. So that's the particle. So your like particle fermions. And then after you did this transformation, so after taking the adjoint and then multiply by I gamma 2, you ended up with the psi2, which represents the negative energy solution, and that's the anti-particle. So this operation, this eta spinner is taking the original particle spinner and then doing some operation on it, and you ended up with the anti-particle spinner. So this operation altogether, I gamma 2 gamma naught, because it's the gamma naught from here, and then all the complex conjugation. This is the C operator. So this is the charge conjugation. So that's how you get from particle to anti-particle. So we talk about like CP symmetry, and this is what we talk. This is what we mean. So take the charge conjugation of your particle, you're gonna get the symmetric anti-particle result, and that's what ETA's physical interpretation is. Cool. Any questions? Nope, all good. Okay. Then let's move on to ABC theory. So this is a toy theory that's very popular when starting Feynman diagrams, because you have a bunch of scalar particles. Scalar particles makes life tremendously easy. Like Feynman diagrams as an idea is not difficult. It only gets difficult because you then have to treat things with like vector and spinor particles involved, and then that becomes like mathematically annoying to manipulate algebraically. So if you have everything as scalars and they're just a number and they don't do anything, then it makes the whole thing a lot simpler to kind of crunch through. So here we just have ABC, and they're all massive particles with some mass that we don't know, but we just define them as MA, MB, and MC. And we only have this one interaction vertex where we couple all 3 particles with this vertex, and the vertex factor is G. So that's the coupling constant. And now we want to consider a process where we scatter AB into AB. So that means initial state AB and then final state AB. What goes on in between is kind of free for all, but it's constrained by what's available in this theory, which is not the law. So draw the leading order diagrams and write an expression for the matrix element. Expression results in terms of the Mandelstam variables. Okay, so we want AB to go in, and then we want AB to come out. I run the other way around, but it doesn't matter. The end states, there's a symmetry. You can flip them if you want. So the only way to make this happen is to use this vertex somehow. And there's only two ways if you think about it. One way is to connect it here, and then so a particle C as a propagator in between, and then couples again to AB. So you have one factor G here and one factor G here. So this one, the propagator C, if you ask what the momentum of the propagator C is going to be, it's going to be the sum of the, so if this is, let's call this P1, P2, P3, P4, the propagator, the particle C doing the propagation is going to have momentum P1 plus P2. And if you recognize, that's the S Mandelstam variable, so the center mass frame. So we call this the S channel. And okay, and then you can easily work out the MS. So that's the what's it called, the matrix element. So you have scalar particles as legs, so they don't add anything; they're just numbers. So you don't pick up any additional terms. And then you go through and you have a coupling G, and another coupling G, G squared, and then you have the propagator 1 over the momentum minus the, so P1 plus P2 squared minus MC squared, so mass of the propagator. And we want to express it in terms of Mandelstam variables, so we can just call this G squared 1 over S minus MC squared. Okay. Yep. And then there's another way to connect the initial and final states together. So if I, instead of connecting the P1 and P2 at this vertex, I connect P1 and P3. So I connect these two states together. So I have P1, P2 here, so I still AB. And then, but I connect to P3 straight away. So that's B. And then C as a propagator comes down this way. And then this one's A, so P4 is here. And here, if you look at, okay, depends on which way you want to curve this middle propagator, you have some time ordering, but it doesn't matter because Mandelstam variable, you can express it either in terms of these two or these two. So you'll get the same result. But if you look at the momentum of this one is P1 minus P3. So that's the T channel. So that means I have MT is equal to G squared 1 over T minus MC squared instead. And we, in general, there technically is another channel, the U channel, but we don't have U channel here because if I want to have U channel, I have to connect P1 to P4. And connecting P1 to P4 means I'll have a coupling that have particle A coupled to particle A coupled with some with the propagator C. And that's not a vertex that's allowed. I'm only allowed to couple A, B, C to each other. So I can't double count A, so I can't connect these two or the B and B to each other. So U channel is not possible in this case. So we don't have these two. So then the total, what's it called, matrix element is just the sum of these two, so MS plus MT. So it just equals G squared 1 over S minus MC squared plus 1 over T minus MC squared. Yep, and that's that. Okay. And now we want to write down the differential cross section, d sigma d cos theta. So if you've done the previous tutorials, and also if you have reference to lecture notes, you can just take the expression. You don't have to rederive the whole thing again. It's the same thing every time. So there's no point doing it multiple times. So we're just going to take the definition we have. So d sigma d cos theta was square root of lambda, the Callan function, S ma squared, mb squared. So in general, it's m1 and m2. So it's your two initial particles. And in this case, we can see that the initial particles are A and B. So we can just label them A and B immediately. Don't have to label them 1 and 2. And then divide by 64 pi s and the flux factor and the matrix element squared. Okay, we can work out the flux. We know what the flux factor is supposed to be. F is just half lambda of half s. Now, normally it's m3 squared, m4 squared, but in this case, because they're all a and b's, so this is the same thing. So this flux factor will cancel out this in the numerator. And then we can just plug in this expression into this m squared. So then overall, we get g to the 4. So g squared here squared again, take that out of the front. 32 pi s, so sub in the flux factor. And then we're going to leave the rest of it in the absolute value. T minus mc squared. And that's our differential cross section. So as you can see, like the phase space integral to get the differential cross section is the same every time. So in a real problem, if you do this for like a honors project or something like that, the hard part is getting this m, is deriving these Feynman rules and working out what these amplitudes are supposed to be. Once you have the matrix element, and then you can plug it into the rest of it. The kinematics is all the same every time. So it's not, that's not the hard part. Hard part is how to get the Feynman rules. Okay, so now we have the cross section. All good so far? Okay. 3, write a mathematical expression for the Mendelssohn variable T in the center of mass frame in terms of energy and absolute magnitude of the 3 momenta and cos theta. So that's just a definition. So this is not really a question. So you just take the definition, P1 minus P3 squared is equal to, so P1 squared is the M1 squared. The particle 1 is particle A, so it's MA squared. And particle 3 is particle B, so gonna be MB squared for P3 squared plus MB squared. And then minus 2 P1 dot P3. Here you want to label 1 and 3 because if you label an A and B and it's not obvious whether it's 1 or 2 or 3 or 4. So when it comes down to the actual 3 momentum, keep the label 1, 2, 3, 4 rather than the particle type. Okay, and then the rest of it is just expanding out this 3 momentum dot product. MA squared. Oh, sorry, that's not a 3 momentum dot product. It's a 4 momentum dot product. Like that. So yeah, the 4 momentum dot product. MA squared plus MB squared minus 2 E1 E3 plus 2 P1 P3 cos theta. Okay, so that's T in terms of the energy absolute magnitude of the 3 momentum and cos theta. So we're here. Yep, okay. (2.4) Okay, derive a mathematical expression for the Lorentz invariant differential cross section d sigma dt. So this t here is not time; it's the Mendelssohn variable t. So it's that's why we did question part 3 to get this t in terms of cos theta. And yeah, hence start with the differential cross section d sigma d cos theta in the center of mass frame, and then change variables from cos theta to t. So yeah, we're basically going to use this expression, change of variables, and the change of variables can be done given this relation between t and cos theta. So given that, I'm going to do it here. So dt d cos theta here, so it's only the last term, so just 2 P1 P3. Okay, and then using that here, recall that we show that you can get from the energy momentum relations that P1 is equal to the Callan function S M1 squared, M2 squared in general. This is in general, 2 root S. And last week we also showed the other one, which is P3. And because you can use the exact same procedure, but then just plugging in the end state particles instead, rather than the initial state particles. So it looks exactly the same, except you get M3 squared and M4 squared. Divide by 2 root S. But in this case, m1 squared, m2 squared is the same as m3 squared, m4 squared. So this would just be a and b, and same, this would just be a and b. So these two are the same thing. And when we plug them into here, we get dt d cos theta is equal to Cannon function, so not square root anymore, so two of these, so put together. I'm just going to simplify this and just call it AB. So that means MA squared, MB squared. And divide by 2, but then cancel out with a 2 on the numerator. So we just end up with 2 and an S. So that's the change of variable. And now if I get d sigma dt is what I want, then I can just take d sigma d cos theta, and then d cos theta dt. Just be that upside down. Okay, so we had a g to the power 4, and then I already forgot what the factor was. 32 pi s and all this stuff at the back. 32 pi s, and then 1 over s minus mc squared plus 1 over t minus mc squared. And then you get a 2s divided by lambda ab from the d cos theta dt. Okay, and then you can just cancel out some of the s's and the numerical, clean up the prefactor. So you get g to the 4, 16 pi lambda ab, 1 over s minus mc squared plus 1 over t minus mc squared, or squared. And that's it. That's that. Okay, all good so far? No one is lost. This is all just kinematics. Okay, if we're all good, then 2.5. Determine the integration boundaries for the t integral. So here, eventually, when we want to find the cross-section sigma, then you can see now that we have d sigma dt, we're going to eventually integrate d sigma dt, and then going to have to find the integration boundaries, and that will give us the cross-section. So here we're trying to find what the t integral boundaries will be for the purpose of computing this integral. So we did a change of variable from before. If I was using this expression here, then this integral will instead be d sigma d cos theta. So then I'll be integrating over the solid angle, not solid angle, the one of the two, either azimuth or the polar angle, one of them. But yeah, so I'll be integrating over this. So I'll be going from like cos theta minimum to some cos theta maximum. And since I did a change of variable, then the integration limits will just change the same way. So before, from when I'm integrating over d cos theta, and if I want to integrate over the entire solid angle, then cos theta will go from -1 to 1. And I just translate that to now what t will be going from. T minus t plus. Okay, so now taking this expression of t and then putting in cos theta equals plus or minus 1, I get that t plus or minus is equal to ma squared plus mb squared minus s plus ma squared minus mb squared s plus mb squared minus ma squared divided by 2s. Yep. So these I just got from the both the center of mass energy and also the through momentum. Okay, and now this will. Oh, sorry, there's one more term behind it. So plus or minus. So these are the energy, and then plus or minus the momentum. So the momentum part will have these through momentum, and then cos theta will give you the plus or minus sign here. So the plus or minus will give you either the Callan function S ma squared, mb squared. So just using the same definition for the through momentum with respect to the Callan functions we had before. Plus or minus divided by 2s. Okay. And now this will just be a lot of algebra to simplify it. And I'm not going to actually do that by hand. What I do is just put into Mathematica how to simplify this. But yeah, just put in this form first. So ma squared minus mb squared all squared minus s squared plus 2s ma squared plus mb squared and this is all over 2s. Okay, and then yeah, you can now put it just through Mathematica to simplify this, or if you want to sit through the algebra. But what you should get is the upper limit, t plus, will be ma squared minus mb squared all squared over s. And then t minus will be 2ma squared plus 2mb squared minus s. So yeah, if you just expand, pick the sign and expand out the full Callan function. So if you forgot what the Callan function is, lambda x, y, z is defined as x squared plus y squared plus z squared minus 2xy minus 2xz minus 2yz. Yeah, and then the terms will either cancel out or different terms will cancel out, and then you're left with these two as your integration limits. Okay, all good. Cool, no problems. Then next part, consider the case where MC, so the mass of the particle that's doing the propagating in between, is much heavier than all the other particles and also larger than the energies involved in the scattering process. Integrate the differential cross-section T over T in this special case to obtain the total cross-section. So we want to now do d sigma dt, and we want to take it in the limit that MC is very large. So if MC is very large, then comparing the terms that where you have 1 over s minus mc squared and also 1 over t minus mc squared, these terms, the s and the t represents the full momentum, so the energy momentum involved. Energy and momentum of the initial or the final particles. And here the question says that the mass of particle C is much heavier than the energies involved in the scattering process. So we can safely say that mc squared is a lot larger than T or S. And in this expression, then we can just ignore the S and T and assume that the 1 over mc squared minus mc squared, this will dominate over the actual momentum term. So when we write down this d sigma dt, we're going to simplify these two as just 1 over minus mc squared. So yeah, if I take the expression I had before, then I'll just have g to the 4 16 pi lambda ab, and then here will be minus 2 mc squared all squared. And then now I can just take it with the absolute value and then square it, then I'll end up getting g to the 4 pi lambda ab mc to the 4. Okay. And then to get the cross section, I'll just be integrating from t minus to t plus of d sigma dt. And that, because there's actually no t left in this. So everything is just a parameter. MC is a fixed parameter. And g to the 4 and 4 pi lambda AB, they all just, they don't need to be integrated over. So you just end up with g to the 4 pi lambda AB. MC to the 4 t plus minus t minus. Okay, so to make this neater, we're going to look at what t plus minus t minus is. So t plus minus t minus is equal to ma squared minus mb squared divided by s minus 2ma squared minus 2mb squared plus s. Okay, putting them all like in the same fraction, then I end up getting ma to the 4 minus 2 ma squared mb squared plus mb to the 4 minus 2ma squared s minus 2mb squared s plus s squared, all divided by s. Okay, the reason I write it down here is that if you look at the numerator, then compare this to the Cannon function. You see, if x is s, and then this y is ma squared, and then z is mb squared, then this matches exactly that. So you got ma to the 4, so ma, so that's x squared, y squared, x squared, y squared, z squared, and then you get all the cross terms in between as well. So when you take the difference between two, you're actually left with the Cannon function AB on top divided by the Mendelstein variable S. So that's pretty neat, because then that goes in here and that simplifies a lot with the rest of them. So putting that back in, your sigma equals g to the 4 pi lambda AB mc to the 4 lambda AB divided by S. So that just g to the 4 pi mc to the 4s. Cool. Okay, so this is actually fairly, like, I wouldn't say common, but it's physically kind of useful. So it's not something that kind of you just make up to make the calculation simpler. So a lot of times you do have interactions where the propagator, so MC, is the one that's like carrying the momentum in between the initial and final states. Sometimes the propagator is a lot heavier. So for example, in any weak beta decay, where you have like an up quark, down quark, and then okay, more like up quark positron. Yeah, I think it's a positron. And then you have a down quark and a neutrino. And in between, it'll be propagated by, oh, sorry, what happened there? Propagated by a W boson. And here, if you look at the mass of everything, the W boson's mass is significantly larger than the mass of the up or the down quark, and definitely larger than the mass of the electron, and significantly larger than the mass of neutrinos. So in this case, you can imagine this to be these two initial state particles, and then when they create the propagator, because you have to borrow a significant amount of energy from the vacuum to create this propagator that is so heavy to make up for the rest mass. And then from the uncertainty principle, that means you have to really quickly give back the energy. So this propagator gets to only go like a very small distance before you start having to decay into the final state. And if you squint really hard and then take the limit that this mass really is a lot larger, then this starts to look like a 4-point vertex. So it just looks like 4 things that are coming together as a single point. So U, D, E plus nu E. So this kind of interaction is easy. So it's like the Fermi's 4 interaction. And yeah, if you can take advantage of this, it does happen, and it does make your life a lot easier. And yeah, it's perfectly reasonable to do what we just did. Okay, does that make sense? Okay, no questions or complaints, then we'll move on to the last question. Okay, consider decay C to AB. So C is considered a heavier particle here. And draw the diagrams after order G cubed. If you downloaded an earlier version, there's a typo. It was saying G squared here, and that's wrong. So it's actually meant to say G cubed. Yeah, so sorry if you downloaded an earlier version of tutorials. Okay, so here we want to draw all the diagrams, and there are in total 5 of them. 5 diagrams. And okay, for decay on the tree level, because we only have one vertex to work with, we only have ABC like this. So on the tree level, we only have one way of doing a 1 to 2 decay. Is to rotate this around, so we get starting initial C particle, and then decaying into a B and an A coupled with G. So this is the only way for us to draw it. There's no other, because we don't have any other vertices to play with. There's nothing else we can do about it. So this is of only order G, since we only have one vertex involved in here. So now the next one is to basically try to make a 1 loop diagram. And 1 loop diagrams are all order G cubed. So there's 4 1 loop diagrams you can make. The first one is you start with the particle C, and then you decay into a B and an A. But rather than letting them just be the end state particle that exits the interaction, you make an additional interaction point here where another particle C connects these two. And then you have particle A and particle B come out here. So you have 3 vertices here. So these two and this original one, so each one of them contributes a factor of G. And that's perfectly legal. If you look at every single vertex, we have A, B, and C legs attached to a vertex of G. So that's perfectly allowed under this APC theory. And here, because we now have 3 vertices, each contributing a factor of G, so this will be order G cubed. So you can see, because this loop, you have to come back around, then all of the 1 loop diagrams will be order G cubed. So now the other 3 loop diagrams are going to be vacuum diagrams. So here you start off with the particle C, and then eventually you get to particle C again, and then you undergo this A and B decay. So this part looks exactly the same as the tree level diagram. So you have just a simple tree level decay. But then on the way to the decay, this C particle kind of undergoes like a vacuum loop interaction. So it interacts with itself by creating A and B pair here. And then this A and B pair then immediately recombines to create a C again. So then from perspective here, it was as if nothing happened and the C particle is just going along its way. But we added in this additional loop to show like it was doing something on its own in a vacuum on this way to the decay. And again, it has 3 vertices. Again, is order G cubed. Okay, and the other 2 are just going to be variations on this. So rather than letting C perform the vacuum loop, we're just going to have C and creating B and then creating A, but then the A particle, before it gets to exit into like a proper long-lived end state, it undergoes a loop decay itself, a loop interaction itself. So it comes out starting as A, and then it creates a C and B pair, and the C and B recombines to create A. And then the last one is just B doing the same thing. So B comes out, loops with itself of an A and C, and then stays as a B and an A here. And all these are order G cubed, because we have 1, 2, 3 vertices. G, G, G. Yeah, so that's the 5 C to A plus B decay up to order G cubed. Any questions?
How do you approach this systematically, or is there no way to do that?
I don't think so. yeah,
So
it's
would
kind
it
of like,
just be practice?
yeah, you just kind of look at, you draw the, you kind of start with a tree level diagram, and then you ask, with the vertex with the interaction vertices that I have allowed in this theory, can I kind of like morph it around? Because once you draw it out, it quickly becomes obvious if it's allowed or not. So it's kind of, at the end of the day, it's still trial and error, but it's not, yeah, it's generally, there's not that many combinations. So hopefully you won't have to sit there forever doing it. But yeah, there's no real systematic way to
Okay,
approach this.
so as long as you're following the rules, then
Yeah, you have to make sure
can
that,
just
yeah,
like
every single
you
vertex
just
follows
try
the rules.
and create new diagrams, as many as you can.
Yeah, people can make an entire career out of this. Yeah, so you create as many diagrams. You generally sometimes have like an experience as well. So if you know you can do this vacuum pair production and recombination thing, then every time you see any kind of these 3-point vertices, then you know you can do that. So if you're given a completely new theory, you might not have seen it before, but if you recognize the same vertices or similar kinds of vertices, and you know at least like on top of your head what you can try to begin with.
Yeah, okay, that makes sense.
Okay. Yeah, okay. Any other questions? That's it for today. So we have done all the questions. So we're actually very early today.
This is kind of far back, but
no.
how do you know like which lines to label P3 and P4? Because like if you'd switch those, like switch, yeah, like you got the P3 and P4 for the T channel diagram, wouldn't that then become a U channel diagram?
Right. So with the Feynman diagrams, you have to first set the initial. So if I say I have these particles, and then, so if I start off with the initial 2 particles and then the final 2 particles, I have to kind of fix the momentum immediately when I start. So if I call this P1, P2, P3, and P4, sorry, then that wouldn't work. So this has to be A and B. And then I start off with the first one, then I do the S channel one. And then if I want to try a different internal propagator, I have to keep these external legs fixed. So these things are not related to the Feynman diagram. They're the initial and final state of the external scenario. So you can't flip those around.
Okay. Yeah.
Yeah.
That
so
makes sense.
Yeah, so when you ask when you can't have the U channel, it's because in order to write this S channel diagram, we specifically fixed these 2. So then I can't flip them later. I see what you mean. So if you call this one 4 and this one 3, is that what you mean? Like if I call this one 4, this one 3.
Yeah, like if
And
you
that
just called them different things.
I think yes, the labels doesn't matter. It's the one way to draw the U channel diagram is to start with the S channel diagram like this, and then you connect it like this. So that's not allowed because of this vertex. But I don't know how to explain this in terms of the labeling. Oh, good question. I don't really remember how to explain it in terms of labeling, but yeah. Let me ask Michael about this actually. Yeah, or you can ask Michael about this.
Okay, all good. Thank
Yeah,
you.
so conventionally, if you see a diagram that's like vertical like this, that's called T channel. U channel is usually one that's like you're crossing the initial to the final state from the S channel diagram.
Right.
Yeah, I forgot exactly why we can, why this labeling is a thing. Okay, anything else? If not, then I'll stop recording now and